Alright, this video is going to be on parametric equations. And parametric equations are used for situations where you can't write a single equation in terms of x and y. So we're going to say used for situations where you can't write a single equation in terms of x and y. And I think there's a few different examples that you could consider with this, but if you're thinking in terms of like x being the independent variable and y being the dependent variable, let's say for example you're like going on a hike or you're like rock climbing or something. If you're talking about a hike where your elevation is changing, you have two different things happening. One is you have a horizontal distance. So that's like I've walked 5 miles or 3 miles or whatever. And then you also have a vertical distance. And so you're talking about, like for those of you who have Fitbits, I don't know if many of you do, but they would talk about like how many flights of stairs you've done the equivalent of. So I go for walks all the time, and when there's this hill that I walk, and if I do the entire thing, it's the equivalent of 25 flights of stairs, but the walk itself is a distance of a horizontal distance of 5 miles. So when we look at this, I wouldn't say that my vertical distance is dependent on my horizontal distance, because that's not the case. So in these sorts of problems, we might say that our horizontal distance is x of t, and we can say that the horizontal distance, or the x, is dependent on how much time that I've been walking or hiking or rock climbing, and then we could say that the vertical distance is also dependent on the time that I've spent doing that. So this is kind of, it's not a terrible example, but I'm sure you can see some gaps in my reasoning. But this is kind of the idea here, where we have one common, they call it a parameter, and here the parameter would be time, and I think that time is a pretty common t value for a parameter. And then we have two different things that we're measuring in terms of that parameter. Alright, so here I'm going to go ahead and write that this is called the parameter that we based our parametric equations on. So we would have one equation in terms of a horizontal distance and one in terms of a vertical distance. And both of these, since it's in terms of t, we would say at time t. At time t. So if you were going to make like a table of values for this, the time would be kind of like the equalizer. So you'd say after like 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, and then you could talk about my horizontal distance was however far I've gone, and my vertical distance is like how far I've climbed up. And so you could have at the time, you would know what those values were. And so I guess I should put of t. So then if you were going to write a point for this, you wouldn't actually even write the parameter out. You would just use the horizontal time and the horizontal distance and the vertical distance, and they would just be in terms of t, but you wouldn't even really, you're not going to think of like a t-axis. You're still going to graph it as an x and a y. So these points, all of the points together, the collection of points is called a plane curve or a parametric curve, depending on the resource that you're using. So one or the other. I think the worksheets that I have call it a plane curve. Alright, now sometimes it's very typical for these for them to define the value of t that you're going to use, almost like defining your domain, because you're defining what you're able to plug into each function. And so it's very common to see a limited value for t that you can plug in. And sometimes we won't restrict it, sometimes we'll use all the values, but typically when you look at a problem, it's going to tell you what the t values can be. Alright, so for a first example, we're going to say given the parametric equation and the value for the parameter, find the coordinate of the point. So given the parametric equation and parameter, find the coordinate of the point. So here, since I'm just saying find the coordinate of the point, that means that I'm only going to give you one t value. So here we're going to say x or x of t, you can write it however you want, is 3 minus 5t, and y is 4 plus 2t, and the value for t that we're going to use is 1. So here, if you wanted to figure out what the x was, you would say 3 minus 5 times 1 is negative 2, and 4 plus 2 times 1 is 6. And so here we have already used the 1, and now we're going to say the point for that parametric curve, or the plane curve at that point, is negative 2, 6. Or here's another example. It seems that we're often going to be dealing with sine and cosine on these, so they might look weird to start, but you'll get used to them. So here I'm looking at this point where t is pi halves, and so if you were to look back at your unit circle, 4 plus 2 cos pi halves, well, pi halves on the unit circle is directly up here, so the cos value there would be 0. So 2 times cos of 90 degrees, or pi halves, this part would just 0 out, and then you get 4. And then if we do 3 plus 5 sine pi halves, sine of pi halves up here would be positive 1. So we have 3 plus 5 multiplied by positive 1 gives you 8. And so that point would be 4, 8. Okay, so next we're going to look at how you could graph these. And first we're going to graph them by hand, and then I'll show you how to graph them on a calculator. So we're going to say graph the curve . And the first one I'm going to say x equals 3t squared, y equals 2t, and then for here, I should not have written it like this, I'm going to say that the t values I'm using are from negative 2 to positive 2. So the t values that we would probably naturally use if this is the interval we have is we would do negative 2, negative 1, 0, 1, 2. I think that's what most of us would automatically go towards. So for my x value, if I do 3 times negative 2 squared, negative 2 squared is 4, so 3 times 4 is 12. Negative 1 squared is 1, 3 times 1 is 3, and then 0, and then 3, and then 12. And then for y, we have 2 times negative 2, 2 times negative 1, 2 times 1, 2 times 2. And so the points that we would be graphing would be 12, negative 4, 3, negative 2, 0, 0, 3, 2, 12, 4. And I'm going to go ahead and cheat. I didn't feel like getting my graph paper out. I don't know if I've shown you guys these before. I have these cute little sticky notes that have graphs on them for when I feel lazy. Okay, so 12, 1, 2, 3, 4. There's 12, negative 4. And then 3, negative 2, and 0, 0, and 3, positive 2, and 12, 4. And you can probably see that those points look like a parabola. If I was to connect these with a straight line, though, we know that that would not look accurate. And I'm going to stop. I almost drew an arrow. I'm going to stop right there because they said the t stops. It's between negative 2 and positive 2. So I should not draw an arrow. I should leave the picture looking like that. Now, this part over here, how far apart your t values are, is called the t-step. So here our t-step was 1 because our t values were 1 apart. So just keep that in the back of your brain. We're going to talk about that more in a minute as we continue looking at these. Okay, we're going to graph another parametric equation. For this one, we're going to say x equals 4 cos t, y equals 4 sine t, and we're going to use t values that are between 0, I almost wrote 24, and 2 pi. I don't know why I was thinking 4. So between 0 and 2 pi. So here, there are a lot of t steps we could have for this problem. I'm feeling a little lazy, so I'm just going to do 0 pi halves, pi, 3 pi halves, 2 pi. I'm going to sketch out a little unit circle so I can think about this. So 4 times cos of 0, the cos right here would be 1, so 4 times 1 is 4. 4 times cos of pi halves. Cos of pi halves up here is 0, so that'd be 0. 4 times cos pi would be negative 4. 4 times cos 3 pi halves would be 0. And then back to the beginning. And then over here, 4 times sine of 0 would be, did I do that backwards? Nope. Sine of 0 would be 1. 1, 0. 0, 1. 1. Oh, 0. Okay. The struggle. All right. So, because that's the point. I should have just written the points out. That would have helped. Okay, and then 0 up 1, that would be 4. And then this would be 0. And then negative 4. And then 0 again. You guys, that was terrible. Okay, and then again, we're going to go ahead and draw this graph. So if I have the point 4, 0, 0, 4, negative 4, 0, 0, negative 4, and then back to 4, 0. Of course, we could connect these straight and we'd have a diamond there, but I'm guessing you can imagine, since this came from the unit circle, that this is actually going to be a picture of a circle. So that's what the graph should be looking like. So that's what those parametric equations would make. So if we want to graph this using a graphing calculator, then what we want to do is we're going to hit the mode button and we're going to use parametric, so P-A-R, parametric. And then now if I hit y equals, it's going to ask me for the x and the y. So first I'm going to go up here. So I've got 3t squared and 2t. And you'll notice we're going to have to change the window for these every time. So you'll notice that when you look at the window, it has all sorts of things that looks different than normal. So the first thing it wants to know is what t values it's in between. So this problem we did was between negative 2 and positive 2. And we did a t step of 1. So I'm going to go ahead and put in 1 and see what that would make the graph look like. For my x values, we went from 0 to 12, so we can maybe go a little bit bigger than that, I guess. We could go like negative 2 to 15. X scale is just meaning that my x's are going to go by ones. For the y's, that might be a little big, maybe negative 6 to 6, and then 1. And so this looks like what we graphed on our paper. Now if you look at this parabola doesn't look super nice. So if you hit your window button and we change the t step so that we were going by 0.5s instead of by 1s, that would give us more points and our parabola would look a little bit more accurate. And then if we did our t step of 0.25, it would give us an even more accurate looking parabola. And then if we did a t step of 0.1, it would be more accurate. So what happens is as your t-step is smaller and smaller and smaller, you're graphing points that are more and more accurate. And so it's not connecting with these straight lines, it's actually connecting them perfectly. So that's just something to keep in mind as you choose your t-step, is usually a smaller t-step takes longer to graph, but it's more accurate. Okay, so if we look over at this one, now I'm going to go ahead and plug this into my calculator. delete, clear. So we've got 4 cos t and 4 sine t. And for the window, we're going from 0 to 2 pi. And we did this in terms of pi halves, which I think you might be able to imagine is probably not going to be the most accurate looking graph. But we shall see. So negative 4, 4, 1. Okay. Yeah. So since our t-step was so big, it made the graph not look very good. So here I could change this. I could maybe do pi fourths. That was 4 pi. I missed the divide. Pi fourths. And then it's a little bit more accurate if I change it to pi eighths. Then we're getting better here. Let's do pi 16ths. Takes a little bit longer to graph, but it looks a lot better. So that's just kind of how the t-step will interact with what you're doing. Okay. Next, we're going to look at, since these are in parametric, is there a way to write them as a rectangular equation? And all that rectangular equation means is it's in terms of x and y. So we're going to say this would be like f and f of x, right? Or sorry, x and f of x, where you have things in terms of f and y, x and y. Oh, sorry. So x equals 3 minus 5t, and y equals 4 plus 2t was the first parametric equation that we looked at. And our goal in these is always to make a recognizable equation. And in rectangular equations, typically we have the y being by itself as the variable that is solved for. So typically we're going to solve for t in terms of x, and then we're going to plug that into the second equation, all right, typically. So here I'm going to say x equals 3 minus 5t, and I'm trying to get t by itself. So I have x minus 3 equals negative 5t, and then I'll divide by negative 5. And you can write it like as a fraction like this, or if you want to think of this as negative 1/5 times x minus 3 equals t, you can do it either way. It honestly doesn't matter. It would just change how you simplify the problem at the end. So now I'm going to say y equals 4 plus 2 times, and then I'm going to plug this stuff I just got in.